Basics of equilibrium. And just to highlight, this is more than just another chapter. This really could have been another unit, but we combined these two because of their size. So we just finished talking about kinetics. Put that aside, pretend we're starting a whole brand new unit. And here we go. Equilibrium. When the forward reaction occurs at the same rate as the reverse reaction in the system, we call that equilibrium. The system is at equilibrium. An equilibrium state can either be physical or chemical. Physical equilibrium. That occurs when you have changes of physical state. And of course, another word for that is phase, and they occur at the same rate. For example, we have a mixture of ice and water at 0 degrees Celsius. That undergoes melting and freezing simultaneously. So that is physical equilibrium. Another example of physical equilibrium takes place between dissolved solute and undissolved solid in a saturated solution. Well, here we go. Here's a saturated solution of copper sulfate, and down here is your undissolved copper sulfate. The two processes, the dissolving, which is one, and the precipitation of the solute, right? Precipitation, you come out of solution, and dissolving is your solid material dissolves into the liquid. They occur simultaneously and at the same rate. Chemical equilibrium, we're shifting gears away from physical. That occurs when a reaction and its reverse reaction proceed at the same rate. When that occurs, we write the equation with a double arrow. So, right, it goes this way and it's going this way. So what we have here is dinitrogen tetraoxide turning into nitrogen dioxide, right? That's this here. Then this way, you have nitrogen dioxide turning into dinitrogen tetraoxide. Dinitrogen tetraoxide is a colorless gas. Nitrogen dioxide is a brown-colored gas. Eventually, the forward and backward reactions reach a state of equilibrium. This means that the colorless gas is decomposing at the same rate at which the brown gas is combining. And hence we have the double arrows there between the two species. When a reaction begins, the forward reaction, which in this case would be up here, the blue, this guy here, okay? You see how it starts. It has a very high rate, okay? Here's the rate, here's time, and then it begins to slow down. The reverse reaction, that's this reaction going this way, and that's down here. It's non-existent at the start, right? It's down here at 0, but then it picks up speed as more product is created and can thus support the reaction going in the backwards direction. Note the line here. That's where equilibrium is achieved. The rates are equal. See how the red and the blue lines are on top of each other. As a system approaches equilibrium, and where is that happening? That's happening to the left of this equilibrium vertical line. Both the forward and reverse reactions are occurring. At equilibrium, the forward and reverse reactions are both still occurring, but they're proceeding at the exact same rate. And you can tell because if you extend this line here to the rate, they both have the same intercept there on the y-axis. Once equilibrium is achieved, the amount of each reactant end product remains constant. However, be very careful. That does not imply that the amount of reactants equals the amount of products. It's just that whatever amount they settle at, it stays the same. It is important to note that equilibrium can be achieved whether you start with the reactants or the products, doesn't matter. However, you do need sufficient material to get both processes going. So let's look at nitrogen plus hydrogen yields azane and also going in backwards direction. Let's look at the first picture. Who do we have? Well, let's see. We have hydrogen and we have nitrogen. We don't have any azane. Okay, see how it's at the 0? The NH3 is at 0. The reaction starts, and which way is it? Starts going this way. Then it starts building up NH3 product, and it starts going that way too, right? And here's the double-headed arrow, and eventually you get to equilibrium. Let's look at this picture here. What do we have? There's no nitrogen and hydrogen, so you have NH3. So clearly, hang on, let me erase this. Hopefully clearly. This time the reaction starts this way until you start forming nitrogen and hydrogen, which then starts the reverse reaction. Until what? Until you reach equilibrium, and then you have the double arrow, where they're both proceeding at the same rate. For the reaction we just showed, where we have nitrogen plus hydrogen yielding ammonia, which of course is a more familiar name for AZANE, you can start with nitrogen and hydrogen and no ammonia, or you can start with only ammonia. Either way, the same equilibrium concentrations of all three substances will eventually be reached. For a reaction to occur, you must have at least a full set of reactants or a full set of products.